Alrighty. Hi, everyone. My name is Draško Profirović. I'm a staff engineer at Pinterest. And today I'll cover SparkMedic, which is our agentic diagnostics tool built to troubleshoot Spark job failures. We'll dive into why we built SparkMedic in the first place, the journey it took from prototype to the current architecture, and the lessons learned along the way. Lastly, we'll end with what's next for us. Bit of background about myself. I had the opportunity to work at a few companies under the data platform org. And despite a lot of differences between those companies, there's at least one similarity: the high bar for providing quality support to partner teams who rely on infrastructure owned by the data platform org. I'm sure I'm not alone when I say support rotation feels like a never-ending stream of questions or problems to resolve. Moreover, it's easy to forget how difficult it is to troubleshoot Spark, or any other distributed system for that matter. And this is particularly true for anyone just getting started with a framework. The other challenge with supporting a load-bearing system comes down to ambiguous priorities. Do you focus helping one team with their failing job, or do you unblock another team with a looming deadline? It's not always straightforward to rank these asks, but as humans, we often have to decide how we'll spend our time. The same is not true for LLMs. Knowledge and capabilities on demand. Our vision for a diagnostics agent was to ask it simply, what did a job fail? And give back a deep research document which provided evidence on the root cause of the failure. The agent would also need to provide suggested fixes that are grounded in the context of the job. Needless to say, this agent would need to be available on all the surfaces where our users operate today. This includes Slack or the Airflow UI, to name a few. We started by exposing our data sources by way of the Model Context Protocol as a way to connect them to the LLMs. At this point, we could start an LLM conversation with the MCP tools enabled and ask the model to reason about the Spark job. This worked in practice, but it required a lot of careful prompting from the human operator. So if you asked the wrong kind of question, it would just go in a totally wrong direction. We extended this prototype by creating a single reasoning and acting agent, which is typically called React for short. The agent was given a single prompt which embodied the problem-solving approach it would take, how to structure the response as a report, and the specific examples on common failure patterns. At this point, we had enough capabilities to start trialing the solution with our beta users. From those early trials, we found a lot of shortcomings with our solution. For instance, prompt tuning became unsustainable. One prompt had to do everything, and adding detail in one area degraded the behavior in another. The response quality was inconsistent. Sometimes analysis was shallow, and other times too verbose. So we really lacked controls to keep the agent on track with what it was doing. We also hit context window issues for production jobs. For example, a large tool output from logs would quickly consume tokens and brought a halt to the agent's reasoning entirely. On top of that, our end-to-end testing strategy up to this point relied on manual tests from production. And this felt anecdotal since production data would get retentioned away anyway. Overall, it was hard to know if changes broke earlier wins. To improve the system, we invested in observability and testability. So we used OpenTelemetry to publish traces to Langfuse. If you've ever worked in a distributed system, this would be very familiar with any distributed tracing platform out there. By viewing the agent's execution as a waterfall diagram of steps, we could better understand the cause of lower quality responses and start to roadmap how do we resolve these. Oops. The reliance on manual end-to-end testing highlighted the need for a more reliable and scalable solution as well. So we ended up building an end-to-end test harness that snapshotted the production state, codified expectations as offline evals, and allowed us to tune our prompt based on the results. So in practice, the end-to-end test harness is quite simple. On the left side in record mode, the agent calls real downstream systems and tool responses are captured as fixtures. These are then saved to the file system and checked in as code. In playback mode, the agent runs against the fixtures instead of the production data, but this time it performs the analysis and generates that report we want. The test suite then grades the report based on the offline evals that we have authored. For instance, an offline eval might check for a limit of 3 suggested fixes. The eval would score lower if the agent provided too many fixes towards managing the verbosity of that final report. Our end-to-end tests allowed us to quantify quality instead of relying on intuition. And as we grew our test coverage, we gained confidence that improvements do not introduce regressions. Once we had the testing coverage in place, we invested deeply in our handling of logs. As probably everyone here knows, logs are really noisy, and many exceptions we see in logs are benign. So simply focusing on the last exception may not always be suitable. Initially, we kept this simple, and we just went with like a heuristics-based approach using regex to filter out certain exception patterns, but naturally, this didn't scale well. Instead, we built an exception classifier pipeline. The core idea was that we would learn which exceptions commonly appeared in successful jobs, treat those like red herrings, and then filter them out in our future analysis. The agent would then fingerprint and cluster exceptions, then rank them based on content relevance and how recently they occurred compared to the termination of the job. We then removed the agent's ability to directly access logs and instead gave it 2 MCP tools. One was the get top K truncated exceptions, which the agent would use initially, but then it would follow up with getting the full log details for a specific exception it found it needed to reason about. This resulted in an improvement to our signal-to-noise ratio and reduced the chance for the LLM to anchor its investigation with misleading exceptions. Like logs, we found that we could improve the quality by investing in how we handle metrics. Raw time series metrics are not context window friendly, and simply feeding your raw data to an LLM works in the small scale, but it fails for any long-running production job. And not to mention, this is horribly token inefficient, so you're going to burn your money really easily. The approach we took was to perform metrics analysis in a quarantined subagent, where we would convert that raw time series data into graphs, which are then collaged into images, and then the appearance of which isn't much different than a Grafana dashboard, albeit we would annotate the graphs with certain useful details like calling out min and max values. This image is then attached to the LLM conversation, and we would prompt the model to reason about the patterns in the data. Images worked really well because we could guarantee how many input tokens would be used for analyzing any given Spark job, irrespective of its duration. Examples of useful signals we were able to get included executors dropping down to 0 or near 0, long plateaus, bottlenecks, or just resource behavior inconsistent with healthy progress. Our subagent would summarize its findings and then return the result back to that parent agent, thereby ensuring the context window was kept healthy. And this really motivated us to start looking at how can we represent the system as not a single agent, but a multi-agent architecture, which is what we did. We overhauled that single React agent into a multi-agent system, and this was built on top of LangGraph's deep agent library. Each agent now had its own dedicated prompt and a subset of MCP tools that it would use. Meanwhile, the deep agent library itself provided built-in tools to keep the agent on track. For instance, a to-do list, virtual file system. And I'm sure this isn't too uncommon since we see this in all of our coding tools like Claude Code or Codex, to name a few. We could finally decompose our single prompt into these specialized roles, and this refactor allowed us to have clear responsibilities for each of these agents. It also gave us a lot of clarity as developers to understand what each agent was doing and how to maintain those prompts separately. We were able to use our end-to-end test harness to really focus in on every individual prompt and tune it particularly. A pleasant consequence of this architecture was that the effort to expand the scope of our project was as simple as adding a new prompt. And this is exactly how we were able to extend SparkMedic to also help users optimize their Spark SQL jobs. Our workflow starts with the user's request entering the system, whereupon intent is classified as either requiring a simple answer to a question or a deep diagnostic session. The triage agent determines the Spark job's lifecycle state. And if it's failed, it'll use a subset of tools to generate a set of failure hypotheses. Each hypothesis is researched in parallel, where we gather evidence to validate it. These research agents then score themselves and return back the root cause that they identified. The supervisor then selects the highest confidence root cause and invokes a healer agent, which is responsible with providing remediations based on runbooks ingested into our vector database. Lastly, that supervisor agent again would assemble the final report, ensuring the proper formatting, and returns it back to the user. What worked really well was the multi-agent architecture. It proved very effective at giving us greater control over the system's behavior. And then the enhancements to our logging led to substantial reduction of inaccurate root causes. We trialed also using LangGraph's workflows as a way to make the agent more deterministic, but this approach proved to be brittle compared to the reasoning and acting agent paradigm. What we're experimenting with now is incorporating user feedback from prior sessions to automatically improve the agent. And lastly, we see a broader opportunity to apply this pattern to other distributed systems like Flink and Trino. The SparkMedic project was made possible by the hard work from these contributors. Thank you for your time.